Okay, hello, hello. Let's get this decompilation going. I have no idea what I'm half doing, but yeah. Ooh. Okay, so let's get started here. I'm trying to figure out what this variable does. It seems to... Honestly, it's a pointer. If I take a look up here, it's variable. It's a pointer right here, you know, it's defined as a pointer, it's an integer pointer. And it points to another pointer here. Pointer pointing to pointer. How ironic. So, what I'm trying to figure out here is... Let's take a look. So, it's being adjusted in these areas, you know. So I'm thinking... I might name it like a generic pointer for now. Just so I can remember that later. There we go, now I can see it around. Generic integer pointer. Ooh, that's a decimal. Actually, that might not be a decimal, that might be hexadecimal. We'll keep it hexadecimal for now. Now, basically, let's take a look. We have our generic int pointer, and we have write module specific register here. That basically just writes to the address that's specific to that certain processor module. Some dispatch from Ghidra. So yeah, we have some system reserved, probably reserving something. Let's take a look around here. So, honestly, this data is assigned to the long parameter. It's a long, which I just called it long parameter. Kind of, you know, ironic. It's a long, but I could just easily fix that. Long. There we go. So this must be a long data, or it could be a memory address. We'll just call it dat address for now. Dat address. And now we have this function, which I will check out later. And, okay, so this variable that's referenced a lot, let's take a look up here, is uFar1. There it is. It's an undefined 4-byte, which if we look at the mapping address, where'd it go? It is, so there's 4 byte types. So undefined 4 basically means it's 4 bytes in size. Now if we look at the data type, standard data type from IBM, we're going to scroll down to Windows here, Windows 64. So there's a few 4-bit we got here, or 4 bytes. An integer, a long, and a float. If you scroll down, you also have a clock, T, and a H file, but I doubt it's going to be any of these. Same with D word. It's most likely going to be float, long, or int. So let's keep that in mind. And with that in mind, we could probably figure out here. So uFar1, let's just follow its path real quick. Let's take a look. So first, it's set to the global descriptor table register. Alright. Interesting. Same, I think this one was also set to the global one. This one was set to the local one, so this we can call the local, actually. This one's renamed wrong. Copy that. We'll just call this the local table register. And then that means this one here can be renamed to the memory table register. You see here it's saying the global descriptor table register. And then you have another interrupt descriptor table register. Which is... It's a path. So, let me think. If I was to... I have an idea. So, if I was to check this out, there's like nothing online about it, because this is like a compiler function, you know, so you're not going to find much about it. But it is a register, you know, so that gives you a little insight of the assembly. And let's see, here's another dat. Let's take a look here. So this generic integer pointer is being incremented by 92, probably to a different address. Most of this is just compiler generated. Ghidra usually points that out. Let's take a look. Shadow stack push, that's a Ghidra function that's pushing something onto the stack. Shadow, silent, 8 bytes. Which, oh, UVAR1. So we have another pointer here. Let's take a look right here. It's a U. It's an unsigned long. So an unsigned long could mean a few things. One, first off, it can't be negative. We know that. And it's a pointer, meaning it points to something. So let's just explore what paths it has. Let's take a look. Okay, so it's assigned down here after this unknown function runs. We can take a look at that later. Pushes address. Okay, now it's used in a statement here. So if this does not equal 0, or the pointer 0, then it'll do all this stuff. Set this U of R. We'll look at that next. So usually U means unsigned. So as you can see here, P for pointer, U for unsigned pointer. So if we hover over, it tells us a bit more. So first, it's a 64-bit pointer. It's 8 bytes long. Pointers automatically add 4 bytes to the size. So that's interesting. Then we have this address here, this AND symbol for address. That equals a -2, but we'll keep that as an address, so we don't want to screw it up. Now, this function runs on the data address. Let's take a look. So it's void. It doesn't return. So quite a few function calls. This is only the entry function or the main function of the kernel, so we're gonna start diving deep into that. Anyways, let's take a look. So it's first assigned here, and then it's set to use long pointer of the function return with the dat address. Ooh. Then we have a pointer long var 7. Okay, so let's take a look at this. Pushes. Googling here. So we have, it's a right shift operator. And interesting. So let's take a look. If we take a look at here, it's saying char A, B, it's pushing A with 1. A1 equals 10. So it basically shifts the binary over. Okay, that's interesting. That's useful. Now we know something. So, since it pushes this variable into, pushes this many into here, we can just call this binary shifter pointer, or shift pointer. That's another basic name we can use. Got dat address. That's gonna be a decimal, because usually if you're incrementing. Same with this. Let's take a look at this. Basically, this is, first off, integer, int, pointer, long pointer. That's doing basic math here. Data address plus this, so it's basically probably incrementing this address here, plus 36, and eventually after it does this quick long math, it increments it plus another 36, and if it equals 0, it'll continue through. So I'm guessing that's the kernel doing memory checks, but I'm not 100% sure, because with memory it's often confusing. I don't honestly code in C a lot. I know a bit of assembly and a bit of like C++, but I mainly program in C#. So I have a fundamental of how it all works, and Google's pretty much my best friend in this, and I learned a lot. So let's take a look here. Another hexadecimal, which is, there's so many pointers here. I don't want to modify these. Ooh, hold on. There's just another simple. Tilde. It means it's a bitwise thing. Okay. Oh, it performs a bitwise not. Okay, that's interesting. Got it. So, basically what this is saying here, where's the bitwise not at? Where do you go? Oh, here you are. So it's basically inverting this one. Alright. It's interesting. So that inverts it. I'm going to quickly save, make sure everything's saved up. Okay. We've gone pretty far. Except this undefined 4 here. It's 4 bytes, but it's not a pointer. So again, that could be anything from int to a long to a float. So if we look at what it does here, global descriptor table register, it's holding a register area, and usually I see registers as an integer, but it can be truly either or. But last time I decompiled something, if I made it into an integer, it would usually throw a warning if it was wrong, or it would continue if it was good. So that's going to be temporary. Oh, we have an AU stack. Allocated. I believe that means allocated stack. I think. I'm just doing a little Googling here. Let's see. It's a return address. So we can just call this stack return address. And it's just an undefined, which usually means it's 1 byte. And that could actually mean a bunch of things. It could mean it's 1 byte, 2 bytes, 4 bytes, 8 bytes, 16 too. But it's, yeah, it's not 16 like usually if it's on a different system. It really just depends. Let's take a think. A little thunk. But on Windows, usually things don't go up to 16 bytes, so it really depends on who you're, or what you're coding on. But I'm on Windows right now, and this is the kernel, so yeah. Anyways, let's continue here. If we take a look at our undefined stack return address, we can rewrite over it. Again, since it's undefined, we can't do anything, but if I want to, I can retype the variable. But for now, let's just take a look. Undefined 8. Again, if we look at our chart, undefined 8. Oh, that means a lot of things. That could be a double, a long double. A pointer is going to be always 8 bytes. Pointer diff, t, size t, time underscore t, and handle. So if we take a look at what this does by using the find again, you can see it's in CRT0. So this is basically a variable that equals. So if it's being equals, there's usually some stuff going on here like integers and stuff. So we could probably look at it being a double, long double. So let's take a look. Just doing some pointer action. They aren't pointers. So I'll say for now, this doesn't seem like it's an undefined 8, so I'd say, can I read to my, okay. Oops, I cannot, it's a fast call. Okay, so I'll say this is a double. Actually, it wouldn't hurt to have a long double. It really wouldn't hurt. You know, long double. Just a few long doubles for our troubles. Get it? Long doubles for our troubles. Okay. Anyways, so now we have our double sets, our long doubles. Now we have to figure out what they do. So I see it as variable assigning. So basically we're assigning this generic pointer address to equal CRT0 after, you know, the pointer area. So basically after the pointer, gets to its new memory address, then we set that memory address to whatever this is, which, if I hover over it, it says it's a compiler, long double now. It's a floating point type, which makes sense. If you hover over this, it'll tell you some things, like what type of letter it could be. Like we got at symbol, B, D, F, which honestly may seem like it's having some meaning. It's possible, but most likely not. So it's just going by memory addresses right now, as you can see, setting it to value. So we can just rename this to mem address 0 and so on. This honestly is probably not the greatest naming scheme, but it's much better than in CR4, which we're just at 3 right now. Okay, there's our memory addresses. This code is very, very screwed up. But we have our binary shift pointer. We have our U-long double, which is good. We want our U-long double, because long double for your trouble. And then after we get the pointer set up and we have the stack return address, now we have to tackle one of these. But I'd like to start with this top variable first, because it's the first variable out of the bunch. So it'd be kind of bad to skip over it. Oh, right here. This is an interrupt descriptor table register, which is a different variable. So we can actually rename this now to global, because the variables, they slightly look different each, which can throw someone off like me. But thankfully I noticed, so we're going to call this interrupt. Bam, interrupt table disruptor. Oh, oopsie, no. That's not the one. I set the wrong one, oops. Interrupt, there we go. So now that we have our interrupt table register, basically it's just grabbing the register, it's taking, setting stuff, the generic int pointer to an address, and then after it sets its address, then the interrupt descriptor table register, this address is now set to that. So the value in that address has now been set, and that's actually really good. It gives us some insight on what these things are starting to do. So basically, what this entry function is now doing, from what I noticed, is instead of me thinking before it would just call a bunch of things, it's actually setting up the stack and stuff, I believe. It's setting up memory addresses, stuff needed for the stack. And this is basically the first thing that runs when you launch your operating system. So, yeah. Anyways, the stack return address is most likely an integer because, it's using an integer. So, let's make this an int. Make this an int 48. Oh, it does not like that. Okay. Undefined 48. What if I just made it an int? Okay, so it's obviously something. So I was to retype and do 48. Nothing comes to mind. Okay, here we are. Not seeing anything for 40. Ooh, undefined 148. Okay. It's somewhere. So it's an undefined 1, which means it's most likely a character. If we look at this, can I turn this 40? I cannot. But that gives us some insight on what it could be. If we look at the function signature, we have a long parameter. Because my naming scheme, it needs some work. The parameter's only used once in an if statement. So I could honestly just return this as an if param. That's shortened. Oh wait, no it's not. So that address is set to the long parameter. See, these things start to get a little confusing until we start renaming things. See, this doesn't have a function you can click into because this is a compile-specific thing, meaning the compiler uses this and links it together, but Ghidra doesn't recognize that. Ooh, what is this as a... Oh, yep, that's not what we want. But yeah. Let's take a look. I want to save it real quick. Let's take a look at this function. Whoa, that's a really big function. So this seems to do a bit more. But if we take a look, let's see if there's anything we can recognize. So we have a debugger. This is 0. Okay. Oh, first while loop. Parameter 1. Let's take a look at this though. This is a void, and it has one int parameter and a long parameter. So we have the int parameter, of course, starting out. So this one might be non-necessary. So let's take a look around here. So we have some bools, of course. We have some integers. This is a decimal. What the hell? What did I just witness? It's not letting me set it. I cannot perform decompiler actions while the decompiler is busy. I wonder what the decompiler is doing. We'll give it a second. Okay, I don't know what it's doing. I think we should still start back at entry. Because it's going to give us more insight on what these functions could do in the future. So that's what we're going to start with. So let's tackle this odd, like, long variable here. Let's find where it's used. Okay. So it's basically saying it takes the value from the generic int pointer, and it sets the binary shift pointer, and then it's used here. So that's interesting. Okay, so it's used in a few areas. Quite a few. Anything else? Oh, we got another. Okay. Do we have another? Oh, we do. Okay. So this tells us quite a few things. Ooh. Okay, so it's then setting probably, yep. It's just adding some stuff. Then it's now set here, which added to 72. And then, ooh, we're setting this back to the DAT address. And then we're setting more. So we're having a minus action here. So that means uvarl7 seems to be either an address or not. Anyways, we're getting some good concepts on what this could be. Now we go back here. So it's a long. It's basically just a value for the registers to use, so we can just call this. It's a mem value, mem long, mem l value. Okay. Now let's take a look. So we have some plus here, which anything with a plus or a minus, you can just probably immediately set it to that. Otherwise, it's gonna be a little confusing later. Because I don't see why you'd add hexadecimal to a hexadecimal to a decimal. Doesn't make much sense. But it happens. Well, we got a negative 94. Just going through saying all the numbers. This is an address. This is an addition, 136. It should be 36. 0xf. That's 15, but Yeah, that's pretty short. Anything that's like significantly longer, like this, I would say some memory address. See, Ghidra automatically, what it likes to do is like swap those over to integers or decimal or binary even I've seen. But it's never usually right. I don't think there's a setting to turn that off. Subtraction. This is setting from a value which appears to be a float. Because I don't know why it'd be that big of a number, so we're going to keep it as this address because it kind of looks like an address. And then we have a not thing here. Let's just find where this is used. Only here. So we can just call this unknown. We'll say dat, unknown dat. But we do know that this is being set to something that's only used here. So it's probably some memory address, so we can just call this one unknown bitwise flip, we can call it. Perfect name. Okay, perfect. Now, we have some things here. This one is an address. This one's not an address. That is a 2. Okay. So this is a, let's do a little Googling here. System reserved. Interesting. So it's a TEB structure. Data structure about the currently running thread. So we can call this current running thread data. Great variable name. Where is this used? Is this used anywhere else? Oh, it is. Only these 2 areas. So it's used as what appears to be a ulong. And we'll say, I'm just going to call this dat address folder for now. Okay, so we got more stuff set. Let's take a look at the rest of these variables here. Now, this one really stumps me in the head because I rarely ever see variables like this. They're used down here. See, now that we have more set, saying that it's an undefined 8, which again, it can be a few things, and those things, just a refresher, can mean a double, a long double, pointer, which obviously it's not a pointer, p, it's not a pointer, diff, it could be a size t, time t, or it could be handle. But noting that this is the kernel, I doubt the handle has been initialized yet, so I'm going to say that's out of the question for now. It's usually initialized later for programs and other kernel stuff. Let's think. Thinking time. Thunk. See what it does. So, first off, pointer data address. Let's take a look. This is a 144 and this one's 152. Okay, we have our stack base here. And then we have, ooh, address not in memory. That's new. That's really new, actually. So we can call this unknown unint address because it's uninitialized. As it says up here, it overlaps smaller symbols at the same address. Okay, let's use var1. Let's copy this real quick, do a little Googling. think. So it basically reads an 8-bit value from memory and stores it. So that's interesting. Okay. 8 bits store. Actually, 8-bit store. Go tackle the first one. That was apparently not the first one, but we tackled a random one. Hold on, give me 1 second. My apologies. So anyways, if we look at the global table... Oh, not the global table. I don't know what I'm... Let's look at this variable. So this is another store value here. So we can call this... Just, we'll say... Let's take a look actually a little more. So it's these two. So pretty much... Yeah, we can rename this to E-bit store 2. Or technically 1 if we want to follow programming naming scheme. Now, let's take a look at these and let's think. So this is undefined for. Automatically go to integer. I don't care if it's wrong. E-bit store. Following our naming scheme so far, I'll say it's a long double. That's pretty much what I do when I have no idea what it could be. Long doubles, beautiful. Now that we have our variable set here, we have a few things. This one's a short because it was originally it was like a undefined 2, which if you don't know stands for, of course, undefined 2 bytes. So, yeah. Now, let's take a little thinking here. We have our stack return address, which we haven't been able to figure out. It is currently used here. And that's it. It's only used here. Which it seems to just be a function return for the stack. And it's undefined. Does it show what type of things are here? It shows a lot of unsigned longs. Let me do a little Googling. Now, let's think. Okay, so let's see. Okay. So I say, using what we've done, this could probably be a handle. Even though it's an undefined 48. Interesting. Okay, so doing a big thunk in the head, we can probably clearly define this is of course an NTO kernel thing. And if we scroll down, we can find it right here. It's an undefined 1, which is usually a char character. So we could probably assign it to something here. Let's find something with 48. I don't know what I clicked. If I search 48, got pointer 48, undefined 48, a bunch of random functions. Like, holy Jesus, there's a few functions. Got structs. It's not a function or struct, so I guess